we are going to start the 6th week of this course. This week we will be discussing the solution of boundary value problems in elasticity. Particularly in this week, we will discuss plane straits and plane strain problems. Okay. Now, let us start with this slide. This is a slide that I have shown several times during this course. The reason being is a very important slide, and it is the core of the analysis that we perform in engineering or in science as well. Now, you see what we have discussed last week is, if this is the representation, this is the difference, these are the different steps. We discussed this, how to write mathematical model for a given problem. So, this step we did last week. Okay. When we derive this step, we did not mention anything about the idealization of the system. What we did mention about the idealization, but in terms of some assumption like the plane, it is a linear problem, material is linear isotropic, the stress strain relation is linear, the strain displacement relation is linear. So, linearity is one of the main assumptions that we used while deriving this equation, but this equation is derived for 3-dimensional continuum. Okay. Now, what we do before we start solving this equation, or rather before we start using this equation to solve several problems in flexure, torsion and so on, let us just go back to idealization of the system, and let us see that this 3-dimensional equation can be, depending on what information we need from the system, depending on the what kind of structure we are dealing with, what kind of continuum we are dealing with, we can simplify these equations. Okay. Because now we can simplify this we can further simplify this idealized system, and that is we are going to discuss this week. Now, all these examples, all these equations are for 3-dimensional continuum, but there are some problems. There is nothing like 2-dimensional problem in real life. Like it is, all problems or all continuum are 3-dimensional. That is, there is absolutely no doubt in it. But there are some problems, there are some objects which can be idealized as 2-dimensional problem. The reason is the one dimension either is very small or the one dimension is either very large, so that the distribution of stresses or the distribution of strain in that particular direction can be neglected. If we can neglect that, if we compare to other component of stresses or other component of stresses, other component of strain, then this problem can be idealized as 2-dimensional problem. So, before coming on to the how to simplify this equation for those class of problems, let us see some of the examples of those problems. Okay. So, for instance, take one example, two example. One is, let us not formally give any name to this example, this kind of problem. We will subsequently do that shortly. Now, you see the two example, there is in this example, this dimension, this thickness of this plate is very small. If this is h, then h is very small. Okay. And where this dimension, if this is L, this dimension is very large. Okay. Now, one dimension is very small and one dimension is very large. It does not qualify any system to be idealized for a particular, idealized as plane stress or plane strain problem, but there are, it depends on the loading condition as well. Now, you see, in addition to that, this dimension is small, this thickness is small, or in addition to that, this length is large as compared to the other dimension. Look at the loading on this structure. Okay, loading on this structure is on this plane. It is, if we take a plane, so all these forces are acting on a plane. Okay, means what I want to say is there is no load if this is, if we take this is the face of this object. So, there is no load normal to this face, there is no load normal to this face. All the loads are acting on this surface. on this surface, and these loads are essentially on a plane, and that plane is this plane. Similarly, here you see all these loads are acting on this. So, there is no load acting in this direction. So, if I take, so there is no load in this case acting in the longitudinal direction. Again, there is no load here acting on the thickness direction, means normal to this plane. Here also normal to there is no load on normal to this plane. Okay. So, load is acting always on this, in this. Okay. So, two things we can see. One is in this problem, the first one, it is the thickness is very small, and the second one is the one dimension is very large. In addition to that, the loading is acting such that there is no loading acting on this plane, on the normal direction. If it is a length, then the normal to this length, in this case it is a normal to the thickness, there is no load. Okay. Now, some example of this, for instance, if you take a plate, and that plate is subjected to the first one, the plate is subjected to in plane loading. This is in plane tension or in plane compression, whatever. So, all these loads, this thickness is very small, this thickness is very small, this h is very small compared to the other dimension, and in addition to that, these loads are acting on this plane. There is no load acting on this. On normal to this, there is no load acting normal to this. Okay. So, loads are also acting on a plane. Now, in this case, what is in this is an example of an aerofoil. Here also you will see, when we see the vibration of all the dynamics of this aerofoil, and now there is no load acting, all these loads are acting on this, in this direction. One dimension is very large, but there is no load acting in this direction, normal, there is no load. Okay. Because if you apply load in this direction, then the things are different. You cannot idealize as plane strain and plane strain problem. Okay. Now, what happens if you have a system, if you have an object, or you are dealing with a problem which has this kind of characteristic? Okay. Now, let's see. Let us start with first this, and then we'll come to this. Take any arbitrary object. Suppose this is any arbitrary object whose thickness is small. This is the thickness, and this thickness is h is very small. Okay. Now, this is the x, y, z direction, and the loads are acting, all these loads, say P1, P1, P2, P3, all these loads are acting on a plane. Okay. Now, we take a small object like a small infinitesimal volume element, and then you take this, let us show the stresses on this volume element. So, you are familiar with this is how the stresses can be represented on this volume element. Okay. This is the coordinate axis. This is the coordinate axis. Now, in this case, you see this dimension is very small. Now, when this thickness is very small, now if you recall that the stresses strain their pointwise description. If you move from one point to other, this their value changes, isn't it? Now, what happens if this thickness is very small? Then what happens, the change in the stress in that particular direction, in this case the z direction, the change in the stress is very, very small. Is so small that you can assume it is constant. Okay. Now, so if we say that the change in stress in this direction is very small, therefore, we can assume this is constant. Now, if this is constant, then if you do not have stress on the surface, this surface is stress free. You recall we said that only stresses are acting on this plane. There is no stress normal to this plane. Okay. So, this normal plane, this plane is stress free. Similarly, the opposite side, if you see, that plane also there is no normal stress, that plane is also stress free. So, we say two things. One is the thickness is very small, and therefore, the change in stress along that direction, whatever, it could be shear stress, it could be normal stress, but the change in that particular direction, the components of stresses, we can assume that no change in that stress. And then second thing is all these two faces are stress free. Then what does it mean? Stress free means there is no stress on that surface. What does it mean? That stress is constant and on the surface stress is 0. It means that along that direction all the components of stresses are 0. But if you apply a force on this surface, for instance, if you take this example of this mobile, now if we apply a load like this and then apply a load like this. This is a plane. There is no load in normal direction. We don't have any load in this direction. Okay, we only have load in this direction and this direction. And then, so this surface is stress free and this surface is also stress free, normal stress in direction. Stress free means there is no stress in this direction. Okay, so and then along this thickness is very small. So along this thickness there is no change in stress. There is no normal stress in this direction, or there is no stress in z direction here, there is no stress in z direction here, and therefore all these stresses, any point you take within this in this object, at that point if you see the state of stress, then all the components of stress in this direction along the thickness direction is 0 or very small, that you can neglect. Okay. Now if it is, then what happens? Then this stress will be 0. There will be no stress in this direction. So this stress will be 0. So this stress will also be 0 and this stress will also be 0. So all these stresses are normal in the z direction. Now you see, if sigma xz is 0, then sigma zx also has to be 0, isn't it? That is what we directly come from the moment balance equation. Now if sigma yz is 0, then this is also 0. Okay. So only stress component that we have, if you take any infinitesimal element at any point, only stress component we have is sigma x and then sigma yy, sigma xy and sigma yx. So the stress component we have is all these stresses are gone. Okay. So these are the stress components we have. Similarly, if we take the other surface also we have sigma xx, sigma xy, and this surface if we take, they are also sigma yy and sigma yx. Now if it is, then the stress can be represented here as this. Now all these stresses, this is the z direction, normal to this plane is now z direction, and this is x direction and this is y direction. Okay. So all these stresses we have only on that plane, on this plane. There is no stress normal to this plane. Therefore, all these stresses are confined in that plane. That is why this kind of problem is called plane stress problem. The component of stresses are only acting on a plane. Okay. Now this is called plane stress problem. Now remember, this is also a 3-dimensional problem, but you can idealize as 2-dimensional problem. Now when you idealize as 2-dimensional problem, the number of stresses that you have to deal with is now less, number of equations are less, so your solution becomes relatively easier. And when you idealize that, you are not if really that assumption is applicable for that particular problem, then the solution you get, which is reasonably good, reasonably represent the solution of the actual system. Now similarly, take another case, this one. Now what happens in this case? Again, the condition is one dimension is small and one dimension is large. It is not the condition. It is, yes, in such cases you may find that, but that you have to decide whether stress and strain in that particular direction can be neglected or not, irrespective of the fact whether this dimension is large or this dimension is small. It also depends on what are the loading system, what kind of deformation that is taking place. Now take an example now, another example where this dimension is very large. Then what happens if you take again a small volume element here, and then on this volume element the strain components will be something like this. Okay. So we have strains on different surfaces in different directions. Now what happens, since this dimension is very large, then the deformation in this direction will be very small, isn't it? Strain in this direction will be very small as compared to the strain in other direction. So, if you apply a load like this, then the material mainly will deform in other two direction. This material may not deform, or the deformation in this direction will be very small. Deformation in this direction will be very small, okay, and the strain will be in this direction will be very small. And therefore, if the strain in this direction is very small, then what are the strain components we have in this direction? We have sigma zz. So, there will be no strain in this direction, there will be no strain in this direction, there will be no strain in this direction. So, similarly, there will be, this will also be 0, and then this will also be 0. So, what are the component eventually you have for this? All these component gone. So, eventually you have, these are the strain components you have. And then what are the, you can represent this as, these are the strain components you have. Okay. So, this is called plane strain problem, because strains are confined on a plane. Now, when we analyze it, this kind of problem, suppose we have to analyze it, then instead of taking the entire problem taking as 3-dimensional problem, we just take a section. Any section we take, we just take a section, and then this section is analyzed. We take a section and this section is analyzed, okay, as 2-dimensional problem. So, we have all these stresses, and on this section, if you take a small element, and this is the representation of the stresses or strain on that element. Okay. So, this is called plane strain problem. Now, for instance, let me give you one example of plane strain problem. Take a scale, and suppose is a cantilever beam, okay, and you apply a load like this, and this bending, it is bending, the bending takes place like this. Okay. Now, you see, this is the length direction, which is the largest in this case, and this is the width of the beam, and thickness of the beam is this. Okay. Now, but if you apply a load like this and if bending takes place like this, you see what happens, all the deformation here takes place either, if you look at across the width, the deformation there is hardly any deformation takes place. What deformation takes place? Only on this plane. The beam is bending, that you can see, that is on this plane. On this plane, if this is x direction, this is y direction, this bending is taking place on xy plane. Whereas in the z direction, which is along the width direction, there is no deformation taking place. Okay. So, if you take either you take this line or you take this line, in both the cases the bending is same. So, along this direction there is no deformation, there is no strain. So, this can be idealized as plane strain problem. But remember one thing, while idealizing this problem as plane strain problem, I did not blindly rely on the fact that one dimension is large or one dimension is small. When you idealize a problem as plane stress or plane strain, you see that how the deformation is taking place, what are the loading conditions, and then you idealized the problem as plane stress or plane strain problem. Just dimension one is small and other one is large cannot qualify some problem to be plane stress or plane strain. Please keep that in mind. Okay. Now, once we have defined what is plane stress and plane strain problem, let us discuss something on. For plane stress problem, we say that stresses in one direction, one particular direction is 0. What about strains? Similarly, for plane strain problem, we discuss that strains in a particular direction is 0. Then what about stresses? Let us find out that. So, let us start with plane strain problem. So, these are the three components of strain in a plane strain problem: epsilon x, and then epsilon x, epsilon y, epsilon xy. All these z components, all these strains are 0. So, essentially the strain tensor you can have like this. You can write as 2D tensor, but all other components will be then 0. The third row and third column will be 0. So, that is why I did not write it here. So, these are the only non-zero components of strain we have. Then what about stresses? Strains are this, that is directly coming from the idealization. But then what about stresses? Is that so that stress in, if strains are 0 in a particular direction, whether the stresses are 0 or not, that let us find out that. Okay, that is very simple. We just write the you recall, this is the constitutive relation, the what is the stress strain relation. On this stress strain relation, if we write the what are the stress strain stress component, let us write that. The stress components are, if I have to write sigma xx, write sigma xx, sigma xx will be lambda, then epsilon is epsilon xx plus epsilon yy, repetition of y, there will be no epsilon zz because it is 0, plus 2 mu epsilon xx. So, this is sigma xx, right. Then sigma yy will be same, lambda epsilon xx plus epsilon yy, and then plus 2 mu epsilon yy. And what about sigma xy? Sigma xy will be lambda, there will be no lambda, this will be 2 mu epsilon xy, right, 2 mu epsilon xy. So, these are the 3 stress components. What about sigma z? We know that epsilon z is 0, epsilon z is 0, epsilon yz is equal to epsilon xz is equal to 0. Let us find out what is epsilon zz. Epsilon zz will be lambda into epsilon xx plus epsilon yy plus epsilon 2 mu epsilon z, but since epsilon zz is 0, so essentially we have this term will vanish. So, your epsilon z will be this. You see here one important point, though in plane strain problem your strain in particular direction is 0, but stress sigma zz is not 0. What about the shear stresses? Let us find out that epsilon you delete this, and then epsilon sigma, you write sigma xz, sigma xz will be 2 mu into epsilon xz. Now, epsilon xz is equal to 0, which will be equal to 0, and sigma yz, which is equal to 2 mu epsilon yz, which is again 0. So, only these 2 components of stresses are 0, but all other component of stresses are non-zero. But remember one thing, epsilon zz, again this, if you substitute epsilon xy and epsilon yy, epsilon xx and epsilon yy from this equation and this equation take this form nu into epsilon sigma xx plus sigma yy. You can do this exercise. Substitute, solve equation number 1 and equation number 2 for sigma, for epsilon xx and epsilon yy, and substitute that in this expression, you get this. Now, what it shows that though you have sigma zz, but that sigma zz can be obtained from sigma xx and sigma yy. So, therefore, you can idealize this problem as 2-dimensional problem, where your unknowns are sigma xx, sigma yy and sigma xy. Now, when you have to find out the stresses in other direction, in z direction, by knowing sigma xx and sigma yy, or by knowing epsilon xx and epsilon yy, we can compute sigma zz. Therefore, we do not need any explicit equation for sigma zz. Only equations for sigma xx and sigma yy will be enough. So, this is for plane strain problem. Okay. Now, let us the same thing. Now, once we have that for plane strain problem, once we understand that only non-zero, these 2 equations are enough. Just now we have seen that we have sigma xx, sigma yy, sigma zz and sigma xy. All these are non-zero, but what happens is, if we know this sigma zz, you can compute this. Okay. And therefore, we do not need any explicit equation in z direction. So, this equilibrium equation becomes this for plane strain problem, and then you can try this. Then once you have the equilibrium equation, then the compatibility equation, the Sane-Venant relation becomes this from the 3-dimensional compatibility equation. If you reduce it and with the only non-zero components of strain epsilon xx, yy and zz, you get this expression. So, this is the plane strain problem compatibility equation. Now, once we combine compatibility equation, equilibrium equation and constitutive relation, we get this the stress formulation. This is the relation we get, and for if you take here also, if it is absence of body force or constant body force, this right hand side becomes 0. So, eventually you have this. We do not need equation for a sigma zz. Here it is actually, when we write it, it is sigma xx. So, this is sigma xx, this is sigma yy. Okay. So, this become this, and similarly if you write the Navier's equation, which is the displacement formulation, then the Navier's equation become this. So, what you can do is, once we know what are the strain components and then stress components, equilibrium equation and compatibility equation, then we have a 3-dimensional equation, general equation for stress formulation and displacement formulation. In that 3-dimensional formulation, substitute the relevant, only take the non-zero term and removing the term associated with 0 stresses and strain, you get this reduced form. Okay. Now, similarly, so this is for plane strain. Now, for plane stress problem, we know that the stress, all the components of stresses in a particular direction is 0. So, essentially your stress tensor become this. It is not a second order, it is not a tensor, second order tensor. If you have to write it, then you have to write the third column and third row as well, but they are 0, that is why it is not shown explicitly. Now, then the same question come, what about strain in this case? Okay. Now, we can compute the strain the same way. We know the relation between strain and stress is this. Recall, in the plane stress case, we use the stress as a function of strain, but now we have to use strain as a function of stress. So, if you substitute that, if you substitute the sigma xx and all this thing, what expression we get is epsilon xx we will get 1 by E sigma xx minus nu into Poisson's ratio sigma yy. Similarly, epsilon yy we will get sigma yy minus Poisson's effect sigma xx. Okay. And similarly, epsilon xy, it will be 1 plus, it will be 2 into, if you write epsilon xy, it will be 1 plus nu by E sigma xy minus nu by E into your sigma xx plus sigma yy plus sigma zz. This is sigma xx plus sigma yy, sigma zz will be 0. And then what you have essentially is this term will be delta ij. Now, this is sigma xy. So, delta ij, this term will be 0. So, this will be delta xy. So, delta ij is a Kronecker delta. So, it is true when I is equal to z. So, this term become 0. This term becomes 0. So, eventually you have this 1 plus nu by E into sigma xy. So, this is for 3 stress components on that xy plane. What happened to epsilon zz? Epsilon zz, if you substitute that here, then what we get is minus nu by E epsilon xx plus epsilon sigma yy. You can try this, and then epsilon xz is equal to epsilon yz, all this equal to 0. Okay. So, then only non-zero term will be, this is the non-zero term, this is the non-zero term, and then this is the non-zero term, this is non-zero term, but again the epsilon zz, once you know these things sigma xx, sigma yy and so on, you don't have to write, you don't need an explicit equation for epsilon zz. Epsilon zz can be obtained from this. Okay. Now, so you can follow the same approach once you know what are the non-zero components of strains and non-zero component of stresses. You can simplify this three-dimensional equation by substituting those non-zero components and removing the term associated with zero components. And similar to plane stress problem, you can derive the simplified form or the plane stress version of the compatibility equation, equilibrium equation, and then the Stein-Venance relation. You can write the same for stress formulation, displacement formulation, Navier's equation, which is. So, you can do that exercise, that I leave it to you. Please do that exercise. Even for plane strain problem, I just showed you the final expression. Please verify whether you are getting that expression or not. If you take any book, all the derivations are given in the book. Okay. So, what we discussed today is, we have discussed that though some of the all the problems are three-dimensional problems, some problems can be idealized as two-dimension, and there are two such idealization. One is plane stress idealization, plane strain idealization. We defined what is plane stress and plane strain idealization, and we have seen what happened to the stresses and strain in these three idealization, and subsequently we have seen what happens to the governing equations for this idealization. Now, next what we do is, we use that simplified governing equation for plane stress and plane strain problem. We try to solve some problems which can be idealized as plane stress and plane strain. Now, before that, one important point you see here, particularly for plane stress case, in plane stress epsilon zz is not 0, right. What it means that if you idealize as a problem as plane stress, you have load. Suppose this is a plane stress problem and you apply a load normal to this, but since the stresses in this direction is 0, but strain is not 0 in this direction, you have a normal strain in this direction. Shear strain in this, all the shear strain in this direction is 0, but you have normal strain on this direction. When you have a normal strain in direction, means you have some deformation in this direction, which deformation is called out of plane deformation. Like it is a plane, but normal to this plane you have some deformation because the strain is not 0 there. Okay. So, this is out of plane deformation. So, the deformed shape no longer remains just a plane, isn't it? So, purely this problem cannot be said, at least the deformed configuration cannot be said, cannot be coined as a plane problem. There is still some out of plane deformation. Next class what we do is, we will discuss more on this epsilon zz and then see how this epsilon zz can be treated, what are the further refinement of plane stress problems, some variants of some different formulation of plane stress problem because of this out of plane deformation epsilon zz, that we will discuss in the next class. And then from the third class of this week, we will start solving some examples on plane stress and plane strain problems. Okay, stop here today. See you in the next class. Thank you.